We are back to statistical methods, and the topic today is a refresher of calculus. But before we start, are there any questions regarding last week's lecture on set sums and functions? Something that you would like to clarify before we continue? That doesn't seem to be the case. Okay, then let's start with the calculus section. And yeah, essentially this is a refresher of high school math. We cover aspects that most of you will have encountered in school, maybe not in your psychology undergraduate, because there usually math is not of that much interest. We need this mainly for two reasons. So one reason is that we will study how we can determine or how we can generate estimators for the parameters of probabilistic models like our GLM. And if we want to do maximum likelihood, we need to maximize a function, namely the likelihood function, and this can be done analytically for the GLM, and hence it helps to be up to date and up to speed what it means to analytically maximize or minimize a function. And the other reason we're doing is because we also will deal with functions that are a little bit more general than the functions that you are mainly used to, namely looking at multivariate functions, maybe even vector valued functions, so looking into multivariate calculus. And finally, to look at integrals makes sense from the perspective of random variables, because certain aspects of random variables, expectations and covariances and correlations, like you know them, are defined in terms of integrals. So it makes sense, if you want to understand what a correlation is, to know what an integral is. And that's essentially in terms of the GLM theory that we're covering this term. These are the main motivations for looking into calculus. Of course, if you look into, if you're interested in computational approaches to cognitive neuroscience, these calculus aspects of course have many other applications beyond the GLM, and they are just very foundational, like set sums and functions and like matrices that we will discuss next week. They even appear in these kind of pure machine learning, where we don't want to talk about probabilities, kind of data analysis approaches. So it's fundamental knowledge that anyone who calls themselves a scientist, be it a neuroscientist or psychological scientist or cognitive scientist, should just know and formalize important aspects of how humans model quantitatively the world. So important fundamental stuff. What do we want to discuss? First, I think I want to talk about derivatives of univariate functions, to remind you of what a derivative is. Then we will talk a little bit about analytical optimization, because that relates to our maximum likelihood approaches. And then we introduce derivatives of multivariate functions, both real valued and vector valued. What that means we will see then. And I think that's then almost it. Then we will discuss some aspects of integration. And like last time, there is a lot of stuff in the script, and there are a lot of examples, and we will not definitely not discuss every little example, so you should study the material obviously in addition to what we are doing here. So I'm trying to give you an overview. If you have already read the material, maybe to focus on the important aspects. If you haven't read it yet, to kind of guide your readings. Good. So let's start with derivatives of univariate real-valued functions. So there is a nomenclature that I use throughout the GLM theory and actually throughout my scientific writing with regards to functions that is helpful in the sense that one doesn't necessarily need to write down the function definition to know what the function is essentially about, and this nomenclature concerns this univariate versus multivariate and real valued versus vector valued functions. We are first concerned with univariate real valued functions, and these are the functions that you know about. So by a univariate real valued function, I mean a function, oops, it's not a equation. I mean a function that takes on or has as its domain real numbers and maps these real numbers again into the real numbers, and that's what it does. So these are the typical functions that you dealt with in school. Something, for example, that you always looked at was something like y equals x squared, so that was understood that you could put in real numbers for x, and what you get out is just again a real number and not a tuple or anything. And we are first concerned with those, and I call them univariate because I can put in a single argument, and I call them real valued because you get out a real number, a real scalar number, not a vector. So we are first concerned with those functions and want to remind ourselves what's the derivative of those. And to this end we consider the derivative of this function, which we denote by a prime, at a location x0, which is just a number. Yeah. So the derivative of a function f at a location x0 is a number, and the question is, what does this number mean? And there I list two basic intuitions. So on the one hand, and this is I think the most important, actually the more important one, f prime at x0 is a measure of the rate of change of f at x0. So the number f prime x0 quantifies how much the function f changes at the location x0. Yeah, so it's a measure of the rate of change, and rate of change meaning the change over a specific interval in the domain of the function, and of course then when you refer to the rate at a specific location, it's the instantaneous change if you want. So if the interval over which you evaluate the change goes to 0. So that's one way to look at it, and that's actually the most useful. So the derivative describes how much the function changes, and that's what it does. The other way you can think about it as the slope, but it's more a pictorial intuition, is the slope of the tangent line of f at a point x0 f x0 in ℓ2. So that's more pictorial line. So this refers to the fact that you kind of approximate the function in a point x0 by a linear function, and if this linear function then is horizontal, there's no change, and if it's yeah, positively tilted, then you have a positive change, and so on. But because that's kind of pictorial, and sometimes if you go into higher dimensions and so on, it's a little bit harder to understand what this pictorially means. I think the basic thing that you should always remember is that the derivative quantifies the rate of change at a location x0. Oops. There is of course a formal definition of the derivative. It doesn't want to do this for some reason. Stay there. So there's of course a formal definition, and that's given by the Newton difference quotient. So if you think about the function f that you can evaluate at x, and you can also evaluate at x plus h, so you go a certain amount further to the right, if you want, in the domain of x, and you subtract from this the value at x, and then you ask, so for example, if you think about distance, let's not do that. Let's not think about distance. Let's just, otherwise I will maybe talk crap. Oops, now it's gone. If you look at the function value at some value x plus h in the domain and subtract from it the function value at the location x, and you divide this by how far you went in the domain of the function. So to here you have obviously the change in the function over the interval between x and h. If you let this interval go to 0, then this limit is the definition of the rate of change at x0, at x, sorry, because we here still have just an x. Then you have the definition of the integral. So the so not the integral, sorry, the derivative. The derivative of x. The derivative of the function f at location x is defined as the limit of this Newton difference quotient, which is this expression, if you let h go to 0. So you assess the change of the function with regards to the change in its input, and you look at this for a very small an infinitesimal, if you want, small change of the input argument of the function. Yeah, that's the formal definition, but of course this requires some ideally familiarity what limits actually are, so it's also a little bit of one can of course discuss this much deeper, and so the basic notion I think is thinking about the derivative of a function as a measure of the rate of change at a specific location is definitely more useful. Good. One thing that is important is in terms of derivatives, this was now defined as a number, as the rate of change at a specific location. If you think about what you did in high school, namely that you computed derivatives, you often evaluated derivatives as functions. And of course one can, based on this notion of a derivative at a specific location, one can define a function namely by allocating to each x0 a value of the derivative at x0, and by this mean define a function of derivatives. Yeah, so these are two things, and one needs to be a little bit careful to not confuse them. So if one talks about the derivative of a function at a specific location, that's a number. If one usually talks about the derivative of a function, one has a function in mind. And actually I have here another way to write this. So this, oops, that's a bug actually in the formal editor. Yeah, I mean it doesn't really make much things much clearer if I write it the other way. But what I want to emphasize here is that on the one hand you can evaluate the derivative at a specific location. You get a number. It's a number, so it's like something like 2.3. That's the rate of change of the function f. Or you evaluate the derivative for all input arguments of the function, and then you have a derivative number associated with each value in the domain of the function, and you have a function again. And this is also what you call a derivative. And we will see a few examples for that in a second. Finally, while we're at it, higher order derivatives can be recursively defined based on derivatives by computing the derivatives of derivatives. And this is also a good point to introduce some notation. I assume most of you have seen this notation. Maybe let's change this x0 to x. Then we have something nice to look at. Most of you have seen this f prime notation. There are other ways to write derivatives. In physics, for example, if you have functions of time, which you often have there, there's actually this dot notation, sorry, which is means the same as f prime. Oops, which means the same as f prime. But we will not use that. A notation that I like a little bit more than f prime and dot is this operator notation, which looks actually like this. So it gets already a little bit questionable whether you do it like this, but I think it's then usually done like this. So that instead of f prime you write df divided by dx. What I write this like all the time is this way, which can also be written like this. It's just notation, but what it says is this is the derivative of f at location x, and it implies some operation, namely that you compute the derivative of f. And based on this notation, it's then fairly straightforward to define higher order derivatives, namely if you have already the derivative of a function, then you can of course apply the derivative again. So if you have this and you say, okay, I want the derivative of this, which is also written more or less sensible like this. So there is not really squaring involved. It's more that the 2 is there to emphasize that it's the second derivative. You have defined here the second derivative of the function f as the derivative of the derivative, and that's meaningful. Of course, for univariate revalued functions, there's also the f2 prime notation. The problem with the prime notation is that at one point, if you compute the 10th derivative, then you have something like this, and that gets hard to count, whereas with this dx notation, you can of course write the kth derivative of a function just by putting the order of the derivative here, and then you have a nice notation for the derivative. Again, this is exactly the same as you see sometimes in math, this notation. These are all different ways to write derivatives. If you go to Wikipedia, you find a nice discussion of where they're coming from and yeah, how they came about. Good, so these were higher order derivatives. Again, if you understand what a first order derivative is, then understanding higher order derivatives is not a cognitive task, because it's just the derivative of a derivative. And of course you can think intuitively about what that means. So of course if you if one thing is corresponding to the slope of the tangent line, then you can start thinking about curvature if you go to a higher order Taylor approximation and so on. But if you're starting out with this, I really wouldn't recommend that. But to have something that you can work with as a higher order derivative, it's just the derivative of the derivative. Now, definitely you have seen derivatives in high school, so a typical example for computing derivatives is, of course, the following. Let's use this here. If you have you, I guess, all know that the derivative of this function is 2x. And you know these rules from high school calculus, that if you have polynomial functions, you take the thing that is in the exponent, write it in front of it, and keep in the exponent the number you have in the exponent minus 1. Of course, these rules for these kind of derivatives follow from this definition in the end, but this is really work that is done in math, so I don't, also in the calculus script, I remind you of all the derivatives that you should have be aware of and that we will need, but I don't prove them. So if you really want to know how this derivative here, 2x of x squared, follows from this definition of the derivative, then you really have to look into a good calculus book to see a proof of that. Of course, in what you can infer based on what we have done here, if you, for example, substitute for x3, then you already know that the rate of change of this function f at 3 is 2 times 3, namely 6. So you also then can infer that if x goes larger and larger, the rate of change gets larger and larger as well. So if you have, for example, 0, then you have the rate of change is 0. If you go to a very high positive number, you get a very high positive change. If you go to a very high negative number, you get to a very high negative change, so a decrease. Yeah, positive rate of change meaning increase, negative rate of change meaning decrease. And yeah, one other example maybe is the derivative of the exponential function. So let's briefly look at that. So I hope you all familiarize yourself with the exponential function. Which was one of the basic functions, and the derivative, and that's a very important fact for a lot of mathematics, is that the derivative of the exponential function is again the exponential function. I actually did with an F in the script. But yeah, so the derivative, if you plot the derivative of the exponential function, you get again the exponential function. What does that say? Well, if you have a very high value of x, the rate of change there is the same as the value that the function takes on. So exponential growth means that whenever you increase something, the increase is even larger. Good, so these are two examples for derivatives that you have seen. What is important actually if you start calculating with derivatives are the rules of differentiation, which are helpful. So let's here maybe put this up so it looks nice. Oops, that's wrong. And these are really helpful if you need to compute derivatives, and the basic rules are the summation rule, so which says that the derivative of a sum of function corresponds to the sum of the individual functions. So I abbreviate this here with respect to the script, so you see these all spelled out in terms of the functions definitions in the script, but I want to go over this quite quickly, so I'm abbreviating this a little bit. So if you compute the derivative of this oops, yeah, no, everything is fine, of this sum of functions of x, where you have n functions gi, then what you can do, it's also referred to as the linearity of the differential operator, you can put the dx in there. Oops. Yeah. So if you have a sum of functions and you're supposed to compute the derivative of this with respect to the input, you can compute the derivatives of all the individual functions and then compute their sum. That's the summation rule. So sums are always good for computing derivatives because you can consider each term in the sum individually. A very important rule for derivatives that we will also of course see is the chain rule. This relates to concatenated functions like we discussed last time. So if you want to compute the derivative of a concatenated function, for example g circ f, like we discussed last time, what that means, then the derivative of this corresponds to the derivative of the outer function at the location of the inner function times the derivative of the inner function at the location x. And this is very fundamental. So essentially this is neural network training if you are interested in neural networks, but this is yeah, that's happens all the time because you often have concatenated functions and your argument with which you are interested in evaluating the rate of change of the function is somewhere in there, so you need to respect the chain rule. And again, the summation rule and the chain rule, they follow, and you can yeah, read about this from this Newton difference quotient definition. Maybe I put this in here because this is fundamental. But again, I'm not proving this here. I'm just saying I'm just telling you that this is the case. These rules apply. There are two other rules which I will now not discuss, which is the product rule and the quotient rule, which tell you how to compute the derivatives of products of functions and ratios of functions. So what do we need this for? One basic aspect, besides that having some general knowledge about these things is of course always a good thing, is analytical optimization. And maybe I spend the rest of this first hour now on analytical optimization. So analytical optimization derives or is a means to evaluate where a function has a maximum or minimum or saddle point, and doing so not by means of numerical computations where you change the input to that function and look whether you reach a maximum or minimum, but by analytical methods, meaning by thinking and writing it down and calculating. And analytical optimization, which we will use when we discuss the maximum likelihood estimator for the GLM, is something that you also did in school. I think you figured out maxima and minima of functions in school. I guess that's still very much something that one does in high school math. It rests on certain aspects that are inherent in the definition of derivatives, and I summarize them here as the necessary and sufficient conditions for extrema. So extrema of a function are maxima or minima, and these conditions are, if first the necessary condition, if there is a maximum or minimum at minimum of, I should say, of a function f at a location x star, let's call it, it's just some x in the domain of the function, then the derivative of the function in this at this location is 0. And this is fairly easy to appreciate. So let's do a little bit of a drawing here. So if you have a function that has a maximum somewhere, then of course it increases and then at one point decreases. So the maximum is obviously somewhere here. Somewhere here, that's where the function has the maximum. And if you now think about what's happening, for example, with the slope of the tangent lines, then of course if you at some point here, does one see that? No. Some point, oops. If you at some point here, let's say, then the tangent line is roughly like this. Almost, but it's definitely has a slope that is very positive. If you go closer to the maximum, the slope gets shallower, and at the location of the maximum, of course, the slope is 0. So the slope referring to the derivative is 0, and once you go away from the maximum to the left, then the slope, of course, gets negative. There you see it. So my slopes are not really where they're supposed to be, but I guess you can infer what I mean. I'm drawing this with my finger. Where's my finger? There's my finger. I'm drawing this with my finger, so I don't have a pen. It's not that easy to do it exactly right. So if there is a maximum or a minimum at that location, of course you can invert the whole thing, then you have the minimum condition, then the derivative is 0. Of course, that doesn't really help you if you want to compute a maximum or minimum, because this only tells you if you have already found the minimum, then you know that the derivative there is 0. But at least if you can find places where the derivative of 0, it can be the case that there is a maximum or a minimum. Or what can also be, there is of course a saddle point, so that's oops, these are points that if you have functions like x to the power of 3 that have this kind of thing, they can of course also have places where the slope is 0, namely here. But this you cannot determine based on the fact that the derivative is 0. But luckily the second and derivatives also have a can also contribute there. So these are then the sufficient conditions. So if the derivative at a location x is 0 and the second derivative is not 0, namely for example smaller than 0, oops, then someone doesn't want to write there, then why doesn't yeah, so if the derivative at a location x is 0 and the second derivative is smaller than 0, then there's a maximum. And of course you also know from high school math that if it's larger than 0, there's a minimum. To discuss this intuitively, I included these plots in figure 3.1 on the analytical optimization of basic functions, where I plot both the function itself and then the first and the second derivative. And there you can intuitively infer why these things hold. So that's if you are, I mean, one thing is that you know that this applies and that you can, like you did in school, compute this. So you compute the derivative, set to 0 and solve for x. The other thing is to understand why there's actually a minimum or maximum, and to intuitively grasp that, and maybe even visually grasp that. And I think this is what you can definitely do based on figure 3.1 and the associated discussion that I offer there. So for what we need of in terms of this analytical optimization in the course is kind of a procedure for computing maxima locations of functions, because we will do this analytically for the GLM. And this then always takes, it's kind of a cookbook recipe that always applies. So you have the function. First thing you do is evaluate the derivative of the function of interest. So for example, if we have a likelihood function, we need the derivative of the likelihood. And then we set the derivative to 0, because if we do that, then we know if there's actually a maximum or minimum at this at a specific location, then the derivative is 0. So if we then evaluate the value of x for which the derivative is 0, then x is a candidate for an extremum. And then it depends. So depending on the function that we are dealing with, for example, if we are dealing with convex, so-called convex functions, then we already know, because all convex functions have, I don't want to say minimum or maximum now, but all, because it's different for convex and concave function. Let me briefly think. Convex should be like this. So they have a minimum at the location where the first derivative is 0. In any case, then we don't have to deal with higher order derivatives, and this is what we will do, and this is how it's typically done in statistics. It always feels a little bit weird. One always thinks that, okay, from high school I know that I now also have to check the second derivative, and this is never done. But it's never done because one assumes that the functions that we're dealing with actually, if one finds a candidate value for an extremum already corresponds to an extremum. Yeah, that's one scenario. The other scenario is that one actually evaluates the second derivative. But this kind of procedure, which I think you applied many times in school, is what we need. So let's briefly do this for to find the minimum of the square function. So let's use this here. No, I want this. So, maybe not this, but this. So let's assume we have this, and we have our square function. Roughly looks like this. So that's here fx that's our function here. Let's make it a little bit colorful. Okay, doesn't look awesome, but has a different color. So that's our square function. If you want to evaluate its minimum, you see that there's a minimum. So we first evaluate the derivative. So the derivative, as we've seen previously, is 2x. Then we set the derivative to 0. And then we solve for x. So we divide 0 by x, and immediately can follow that x is 0. So x is 0 is now candidate value, and in this case we can of course also look at the second derivative, which is 2. So we see that the second derivative is 2, so it's larger than 0, so we have a minimum. Yeah, so that's the basic logic of analytical optimization, and this is what we will then need later on if we are kleiner radiere. I want to get rid of this here. If we are computing maximum likelihood estimates. Good. So this was essentially just a refresher of things that you have seen before. Of course, if you study math, you will spend like a full term on introducing derivatives. So of course, this is just a brief reminder of things that you know about. A little bit more discussion and definitely more examples you find in section 3.1 and 3.2 of the script. But is very focused on what we will need later on. So in the second hour then I would like to first discuss derivatives of in multivariate calculus, and then briefly talk about integrals. Are there questions right now? Okay, that doesn't seem to be the case. So let's have a break until 10:30, and at 10:30 continue with some basics of multivariate calculus. Okay, then let us continue with some refresher of some calculus, and maybe now even not only refresher but also something you haven't seen before. But before we continue now with derivatives of multivariate real-valued functions and then multivariate vector-valued functions, are there any questions regarding the first hour, something that you would like to clarify? That doesn't seem to be the case. Can you hear me?
Yes.
Okay, so there are really no questions because you can hear me. Okay, then let us continue with the introduction of some essentially notation for the case of multivariate real-valued functions. So first of all, what do I mean by these functions? These are functions now which are not functions of a single scalar argument, but which are functions of tuples of real numbers or vectors, as we discussed last time, because we just call these vectors even if they are not formally embedded in a vector space. So here the idea is that we have an n-dimensional vector which gets mapped onto a scalar real number, which means that our x is of the form x1 to xn. So you can either write it like this. I mean, you can also, to make this fairly explicit, also just write it like this. Then it's made explicit from the very beginning. But if you just call this a tuple of n scalar numbers, you call that x, then of course that looks as did univariate real-valued function, but because here this is the space of n-dimensional tuples, it's implicitly understood that this is a vector. So just to make this clear by example, one example for such a function is, for example, such a function let's do it differently so then it's clearer. And now x has three components, three entries, and for example we define f of x as the first component, plus the second component minus the square root of the third component. So if we evaluate this, we get a real number, so just a scalar real number, but what we put in is a three-dimensional vector which has components. Maybe I write this vector here so that you're clear about this. This vector here is x. With x1, x2, and x3. But of course this is clear because we have here R3. Now these are functions that are ubiquitous in statistics, machine learning, AI, wherever you look, and they are just ubiquitous everywhere. I think in physics they are called scalar fields because to each n-dimensional vector you allocate a scalar. So, and physics like to have fancy names for things, so physicists, they call these things fields, but for us these are just multivariate real-valued functions. And often in statistics and machine learning, these multivariate real-valued functions play the role of cost functions. So you have some model that you want to optimize with respect to a set of parameters, which is then not just a single scalar parameter, but maybe all weights in a neural network or all beta parameters in a GLM. And to measure how good you are doing this, you use some cost value, which is then usually just a single scalar number that says if it's 0, it says very good, and if it's larger than 0, it says can be improved. And you want to minimize such a cost function, or you want to, for example, in maximum likelihood, obviously you want to maximize a likelihood function, which is, and a likelihood is also just a scalar number. So these functions often play the role of cost functions. And to now figure out where they have a minimum or a maximum, one of course also needs the notion of derivatives here, and this requires first the introduction of partial derivatives. So we first need to define the partial derivative. So partial derivatives, as opposed to standard derivatives, are denoted with this somewhat fancy symbol here, which is partial if you look at its LaTeX code. The partial derivative of such a multivariate revalued function just corresponds to the derivative of fx as a function of, oops, maybe I should put this up here, of xi only, so all x j j are treated as constants. So that's one way to define the, or that's not even a definition, it's more like an explanation of the partial derivative. So the formal definition I don't want to do here. But what this means in terms of computing the partial derivative of a function is that, for example, if you want to compute the partial derivatives of this function here, you first need to think about how many there are. There are as many as there are input components. So there is the partial derivative with respect to x1, with respect to x2, and with respect to x3. So there are 3 partial derivatives of this function. And if you want to evaluate the partial derivative of fx, let's say with regard to x1, you treat x2 and x3 as you would do constants in standard derivative. So standard derivatives, if you have a function, so let me just for a moment put in other symbols here. If you have a function like this, f of x is x plus a minus square root of b, you would know how to compute the derivative immediately. You would say, okay, a is a constant, the derivative of a constant is 0, the derivative of another constant is also 0, and here we have I just need to compute the derivative of x1, and that's 1. So the derivative of this function with this function here of x is 1. And this is how you should think about when evaluating partial derivatives, because the partial derivative of this function with respect to x1 means that you consider x2 and x3 constants. So if you evaluate the partial derivatives or partial derivative of f with respect to x1, the derivative this here is actually 0, and this is also 0, and you get a 1 here. So again, like higher order derivatives, partial derivatives can be reduced to the standard derivatives that you are familiar with and have applied many times in school. You just need to adhere to the logic that if you compute the partial derivative of a multivariate function with respect to a given input variable, you need to treat all other variables as constant. And this is discussed with some examples in the script. Yeah, that's, I think, as much as I want to say about that. Again, you can read more about the formal definition of partial derivatives and maybe its visual intuition, that you keep everything constant and go only in one direction, in math books. But I think to get used to this idea of partial derivatives, it's important to compute some partial derivatives and maybe plot them, this is just works just by means of appreciating that they can be reduced to the standard derivatives you have been dealing with since you were, I don't know, 12, 14, I don't know when this starts in school, don't remember anymore. Now, when you have partial derivatives, you can also, like for standard derivatives, compute higher order partial derivatives. But the problem is then that, of course, if you compute the derivative or derivative of a univariate real-valued function, then it's clear with respect to which argument or which input you do that, namely with respect to x. If you have partial derivatives, you can, of course, compute the derivative of a derivative with respect to either the same or a different argument. So, for example, the second order partial derivative of a multivariate real-valued function is, like previously, is the derivative of this partial derivative, and this just means that you then consider whatever you get out here as a function of xj, and this is also denoted, so this is again just notation, as this, or by this. And then a fundamental theorem in multivariate calculus says that the order in which you apply the partial derivatives does not matter. That's called Schwarz theorem. I'm not obviously proving this here, but this is the same as first computing the partial derivative with respect to xj and then with respect to xi. So that's the same. And one thing more, yeah. So if x and y are the same, if y and j are the same, then you can also write this as this partial square and then partial xi square. So this relates to the fact that the Hessian matrix is symmetric, but we will see that in a second. Okay, so this is just higher order partial derivatives. Again, it's the same. So what I'm trying to do here is to, of course, show you how simple all of this is, because you know what a derivative is, then you also know what higher order derivatives are. You know what a derivative is, so then you also know what partial derivatives are, and if you know what a partial derivative is, you also know what a higher order partial derivative is. So it all can be reduced to the basic rules of differentiation that you learned in high school. What one can do, and this is now more basically kind of summarizing these things, is define summaries of these partial derivatives, because if you think of a function, a multivariate real-valued function, then of course you can compute n partial derivatives. So you can compute, doesn't want to do it. for each I from 1 to n. And a summary of these partial derivatives that you can compute is the so-called gradient. And the gradient is denoted by a nabla sign, so that's some fancy notation, nabla f. And this gradient, if you view it as an operator, associates with each value in the input space of f, so in the domain of f, another vector, and this vector is just the vector of all partial derivatives. So let's take this one. So if you just compute the partial derivative of f for all oops. Sorry for that. Always jumps a little bit back when I adjust it with my fingers. If you compute the partial derivatives with respect to... Oh, I pressed something. Sorry. You should still be able to hear me. If you compute the partial derivatives with respect to all components of the input and you concatenate them into a one list, so a column vector, then you call this the gradient. And the gradient, yeah, is kind of like if you want a summary, or it's a summary of all partial derivatives, and hence roughly analogous to the first derivative of a univariate real-valued function. Yeah, so in a univariate real-valued function you have the derivative. In a multivariate real-valued function you have the gradient. It's not quite correct, because actually the better summary of the first derivative of a multivariate real-valued function is the Jacobian matrix, which is actually the transpose of the gradient. So not writing everything as a column vector, but writing everything, writing all partial derivatives as a row vector. But if you start out in computational approaches, I think because you come across the gradient much quicker than you come across the Jacobian, although we will come across the Jacobian in a second. But when you read like books on numerical optimization and so on, and machine learning, you will come across the gradient, and also we will need it for the likelihood effect, for the likelihood maximization early on. Come across the gradient more, and then it makes sense to intuitively think about the gradient as the first derivative of a multivariate real-valued function, which is also not completely wrong. It's not completely precise, but it's a good first approach. And similar to the first derivative, one can actually also collect all second order derivatives in a matrix. So I know that we don't really know what matrices are yet, but as we will see, matrices are just rectangular grids of numbers, and if we sorry, that was wrong. If we now consider all second order partial derivatives that we can compute for a given function, then of course we can compute the first derivative with respect to I being 1 to n, and then we can do for each of those, can again compute with respect to I to n when we compute the second order derivatives. And if we if you put all of them together in one array, we get an n by n array, which looks as follows. Oops. No, come on. Which which looks as follows. So we're now dealing with second order derivatives, so things like this. And if we put all of those where as the second derivative we go from 1 to n, and put all of them where we put the first derivative with respect to x1 into the first row of this array, then we get what is called the Hessian or Hesse matrix. And this Hesse matrix is then on first approximation identical to or the generalization, if you want, the generalization of the second derivative of a univariate real-valued function. So the bottom line of what I've just shown you here is that first, so if you have a univariate real-valued function, you have the first derivative. If you go to a multivariate real-valued function, you go to the gradient. Although formally correct, it's better to go to the transpose of the gradient, which is the Jacobian. And if you have the second derivative of a univariate real-valued function and you generalize this for a multivariate real-valued function, you go to the Hessian. Good, so these were derivatives of multivariate real-valued functions and the associated concepts of a gradient and Hessian. And now, before I hopefully find a little bit of time to talk about integrals, maybe not, let's see. What we also need are derivatives, or at least the first derivative of multivariate vector-valued functions. Now, what do I mean by multivariate vector-valued functions? Well, I mean functions that map vectors onto vectors, hence vector-valued. So these are functions that take in vectors and return vectors. And here it makes a lot of sense to write out to see what this actually entails. So these are the values that these functions take on. Are vectors, and they have as components the so-called component functions, and the component functions themselves are then again multivariate real-valued function. Yeah, so this function f1 here is a multivariate real-valued function, so it maps a vector x to a scalar, and these component functions make up the multivariate vector-valued function. And now there is no need that there are as many component functions as there are input values. So this can sometimes happen, but there's no need. Hence, we have n component functions and m component functions and n input values. Somehow can optimize where I put these things, because I'm always interfering. I'm always interfering with the WebEx there. That's what I want. So this is how multivariate vector valued functions look like. So just to give you an example, if we have a function f from 3-dimensional space to 2-dimensional space, real space, we could, for example, have something like this. So the first component function, let's say, only takes the first two input arguments and evaluates the sum. And the second maybe takes the product of all three. Yeah, so we put in a 3-dimensional thing and we get out a 2-dimensional thing. It can also be, so there's no restriction here that the input needs to be larger than the output. You can also have a 2-dimensional, a 1-dimensional thing and get out a 10-dimensional thing by maybe just reproducing the same thing over the 10 component functions, the input argument. Now, the last thing, or what is important with respect to these multivariate vector valued functions, of which of course multivariate real valued functions are a special case where there's only one component function. The last thing I want to mention about those is that we can also define their first derivative, and that's called the Jacobian matrix. And the Jacobian matrix is defined as follows. It allocates to each value in the input space m times n matrix. So m is the number of component functions, so the dimensionality of the output argument, and this is defined as follows. It's the matrix of all partial derivatives, so in this sense it's very close to the gradient. No. Of all component functions. So again, this is just an array of numbers, because we formally don't know what matrices are yet. So we just define a rectangular array with many numbers, and these numbers correspond to the partial derivatives of the component functions laid out in a specific grid form, which here means that we go over rows for the component functions and we go over columns for the partial derivatives. So how this looks like then is as follows. Let's use this one here, then we don't have to create everything de novo. So we stack, of course we are not dealing with second order partial derivatives here, but with single derivatives. So we have the first partial derivatives, and we apply it to the first component function in the first row of this matrix, and we go over the input arguments in each row, and across rows we go over the component functions. So the last thing is that we're looking at fm, and also for fm compute all the partial derivatives. be a little bit funky here. There's some, this is my other thing that I created. Go away. So that's the Jacobian matrix, and this is the first derivative of a multivariate vector valued function, so corresponds to the first derivative of a univariate real valued function. And actually the gradient of the Jacobian matrix for multivariate real valued function corresponds to the gradient. So if you think you have only one component function here, then of course you only have the first row here, and if you transpose that, you are back at the gradient. And actually it turns out, if you look at a little bit more into multivariate calculus, that it makes more sense to consider as the first derivative the Jacobian matrix. Good. So these were basically just a bunch of definitions for multivariate calculus. So what you should definitely remember are the definitions of what is a univariate real valued function, what is a multivariate real valued function, what is a multivariate vector valued function, and what their respective first derivatives are called, and for the multivariate real valued function, then also the second derivative. We will come across these things again, and the part of this lecture is just to introduce these definitions, so that later on you know what I'm referring to. Good. And yeah, then the last thing is actually the notion of integrals. And we have a little bit of time, and I think actually the time is enough. I mean, you have the script, so you can read about integrals again and remind yourself there. So the last thing I want to remind you then of today is the notion of an integral. Let's make this bigger. And basically also remind you of two fundamental aspects. So first of all, that integrals are in the sense of definite integrals. They are just numbers, and we will need this notion when we talk about the expected values of random variables and things like correlation. There we compute definite integrals, which are numbers, and they are denoted like this, and they are approximations, as you hopefully know from school, or they are not approximations, but you can approximate integrals by these Riemann sums. And I will make a little drawing in a second. So the basic notion of an integral is the area under the curve, as you hopefully know from high school math. So if you have something like this, and then you have then you have a function. Oops, weird function, but nevertheless a function. You have a function, and you're referring to some integral. Then what the integral corresponds to is the area under the curve. And here we have A and B. And this corresponds to the, or you can approximate this area by putting in these rectangular areas in here. So these are these values f of xi, delta x, where this xi is somewhere in, or where, for example, the xi is at the left boundary or in the middle of these. And if you make the width of these rectangles smaller and smaller, then you get to the integral. So I assume that you are fairly familiar with this idea. So there is a formal discussion of that in the script. So the approximation is laid down a little bit more in depth, and I thought there was also some. No, that's just the intuition that is used there. What is a little bit maybe less common and what you haven't thought much about is that there's also the notion of indefinite integrals, which are what you I guess know as antiderivatives. So if you ever computed integrals in school, you know that you needed to compute the antiderivative Stammfunktion and then subtract the value of the upper interval boundary evaluated at the antiderivative. You needed to subtract the value of the lower boundary of the interval from the value of the upper boundary of the interval evaluated for the antiderivative. So it was always compute the Stammfunktion, compute the antiderivative, and then put in the interval boundaries and subtract antiderivative of b subtract antiderivative of a from antiderivative of b. So fb minus fa. Now, formally, this can be introduced like this. So the antiderivative of x is that function for which the derivative, so f prime of x, is given by the derivative of this integral here. So the point is that, of course, you know that the derivative of an antiderivative is just the function itself, because that's how you find the antiderivative. So the antiderivative Stammfunktion is defined as the function that, if you compute its derivative, gives you the function again. And this corresponds, of course, here to the computing the derivative of the integral of the function from some lower boundary. Here I put 0 to x, and this should be an s, sorry. So this then leads to the notation f of x as the integral which is more or less clear. So I spent some time thinking about what this is actually supposed to mean, and in the script I put in a proof of this equality here based on the book by Leithold, which tries to make this meaningful, because the question is a little bit, these are all fancy symbols, so what is this really supposed to mean? And if you look into this proof and are happy with kind of discrete versions of this, and you are happy with, I think, the mean value theorem, which is something that I don't discuss here, comes in at one point, then you have a good chance to understand formally what this is actually supposed to mean. Informally, of course, the notion is the antiderivative is the function that, if you compute its derivative, gives you the function back. And then if you want to compute some integral, you can use the fundamental theorem of calculus. So let's stop on this one, which you used many times in school, namely that this integral can be computed as v and f is so for the antiderivative of f, you can compute this integral by subtracting the value of the antiderivative at the upper interval boundary minus the antiderivative at the lower integral boundary. And also this fundamental theorem of calculus, which is very familiar because used in school, is formally derived and shown to hold in the script. So if you want to get a deeper understanding of that, please have a look at that. Finally, there are some, somehow I find this a little bit ugly, so anyway, let's keep it there. There are some properties of integrals that we will need a lot, so I want to mention them. Namely, I think it's actually only the linearity property. So if you compute diese neuen Medien, kann sein, was das alles nicht. If you compute the integral of two functions, f of x plus g of x dx, then you can split this into the integral of f and the integral of g. And if you compute, so that's the linearity of integrals, if you compute the integral of the scalar multiple of a function, then you can evaluate this as, so you can take the scalar multiple out as the integral of as a times the integral of x. So these are the linearity properties of integrals, which we will use a lot when we talk about expectations and covariance and correlations. Finally, there are some basic basic antiderivative rules in the script, so have a look at them. Once we start computing integrals, you might want to look them up again in any case. Good. And finally, I put in also the notion of double integrals or higher order, double integrals or integrals with respect to multiple arguments into the script, because we also sometimes need that. But again, like in the case of multivariate calculus, these always reduce to single variable integrals, so there's also not much new there. Good. So now this concludes my brief run through a lot of calculus material. I try to focus on definitions and introducing the basic entities that we will be dealing with. Of course, you can spend and should spend more time in looking at examples of all these things, and looking at examples and trying to, for individual examples, clarify for you what these mean. We will need all of them, so make sure that you have a good understanding of them.